This is section 5.5 in your text, the pigeonhole principle. So suppose we have a flock of pigeons that fly into a set of pigeonholes to roost, and if we have more pigeons than pigeonholes, then it stands to reason that there's got to be at least one pigeonhole that has more than one pigeon in it. So as we can see in my beautiful picture, here I have 7 pigeons but only 6 pigeonholes, and therefore there must be 2 pigeons in one of the holes. If I had 9 pigeons, you get the idea, there would still be more than one in at least one of the holes. That is what the pigeonhole principle is all about. So the pigeonhole principle essentially says if you have k plus 1 or more objects that are placed into k boxes, so essentially we're saying one or more objects than boxes, there has to be at least one box containing 2 or more objects. So again, that's pretty straightforward. So for example, let's say you have 367 people in a room. Well, there must be 2 people that have the same birthday because there are 366 possible birthdays. In a group of 27 English words, at least 2 must start with the same letter because there are 26 letters in the English alphabet, and if there are 27 words, at least 2 of them must start with the same letter. So of course there is a mathematical way to determine this. So if we're trying to determine n objects in k boxes, where obviously n is greater than k, then we can say that there's at least one box that contains n divided by k, and this is called the ceiling function. And remember, the ceiling function just tells us to round up to the nearest whole integer. So for instance, I had 27 English words divided by 26 letters in the English alphabet. This number is a little bit greater than 1, and this ceiling function says round that to 2. So we know that at least one box contains 2 objects. If I had my 367 people in a room divided by 365, again, this value is greater than 1. Greater than 1 says round up to 2. So at least 2 people in that room must have the same birthday. So here are a couple of questions for you to try. Again, these are pretty straightforward, easy examples of the pigeonhole principle, and then we're going to get into some that are a little bit more complicated. But I'd like you to press pause and try both of these questions first, and then press play to see how you did. So again, among the first 100 people, what is the number of people that must be born in the same month? So if it's in the same month, we're talking about the ceiling function of 100 divided by 12. That's how I would go about solving this. So 100 divided by 12, rounded up to the nearest whole integer, is 9. So there must be at least 9 born on the same month. How many students in class must there be to ensure that 6 students get the same grade? And of course there are 5 grades. Now this one's a little bit different because we're still using this pigeonhole principle and the ceiling function, but I don't know n. So I'm saying n divided by the 5 grades has to be equal to 6. That's essentially what I'm solving for. So it's not as easy as just saying, well, 5 times 6 is 30, so it's got to be 30, because remember, it's anything that rounds up. So if I said n was 25, well, 25 divided by 5 is exactly 5, ceiling function or no. So the lowest number must be 26. So the lowest possible value must be that n is 26, because 26 or more would mean that 6 students would get the same grade on whatever assessment they are taking. Before I set you loose on a couple of questions that will maybe stretch your brain a little bit, I want to go through just a few more with you. So let's say I have a bowl. I've got 10 red and 11 yellow balls in the bowl. So 20 balls, 10 red, 10 yellow. A says how many balls must be selected to ensure 3 balls of the same color. So I can look at it 2 ways. I can say let's look at the worst case scenario, which means the most number. So to get 3 balls of the same color, I could say my first one was yellow, My second one was yellow. I don't want to pick another yellow yet because that's not worst case, that's best case. Then I get a red, then I get a red. At this point I'm stuck because whatever I pull out next, yellow or red, that's going to give me 3 of the same color. So the answer is 5. So I can do it without using the ceiling function. Or, in this case, I can still look at the ceiling function and say there's 2 colors, which is essentially 2 boxes. So I'm saying n divided by 2 has to be 3. So what does n have to be? Well, 4 divided by 2 would give me 2. 5 divided by 2 would give me 2.5, which rounds up to 3. So n must be 5. Now this one, not quite as straightforward because now I can't just rely on the ceiling function. We're not just saying ensure 3 of the same color, we're specifying 3 yellow balls. So again, I'm going to look at the worst case scenario, or what's the most number. Well, it could be that my first 10 balls are all reds, and then I get a yellow, and then I get a yellow, and now I'm stuck because now there's no more reds to take out, and the only thing left is a yellow, and so it must be 10 plus 1 plus 1 plus 1, or 13 balls. So that's the worst case scenario. The next 3 slides all contain questions that I'd really like you to struggle with a little bit before you go through the answers with me. So what I would suggest doing, if you are actually enrolled in my class and not just watching this video for fun, is actually trying these questions on your own, collaborating with your classmates in the Teams environment to try to come up with the answers to these before you just press play and see what the answers are. Because it's much more beneficial for you as a student to actually have tried these and to struggle with them a little bit before you just find out what the answer is. So here's the first 3 questions. Again, I would press pause, read the questions, try each of them, work with other people. When you're all done, then you can watch the video to see what the answers are. So for the first one, what is the minimum number of students, each of whom comes from one of the 50 states, must be enrolled in a university to guarantee there are at least 100 who come from the same state? So again, we're saying that that number must be 100, and they're asking for what is n for this to be true. So we've kind of looked at these before, but we didn't really talk about what's the math involved and how to get there. So what I can really do is I can take this number and subtract 1. So instead of 50 times 100, take 50 times 99, because 50 times 99 would give me 99 here, and then add 1 to that. So 50 times 99 plus 1 is 4,951. That is the minimum number of students to guarantee at least 100 come from the same state. Part B. There are 38 different time periods during which classes at a university can be scheduled, and 677 different classes. How many rooms will be needed? This one's real straightforward. Ceiling function, 677 divided by 38, and that gives us 18. Last one. Computer network consists of 6 computers. So we have 6 computers. Each computer is directly connected to 0 or more of the other computers. So again, we think, what are the number of pigeons? What are the number of boxes? Well, we know that I have 6 things, and the question is, what's the number of connections? Well, if it's connected to the other computers, obviously we're not going to have a computer connected to itself. So 5 is the most number of connections, because we could have 1 connection, 2 connection, 3 connection, 4 connection, 5 connections. So essentially I'm taking the ceiling function of 6 divided by 5, which is 2. If I round up, that's the ceiling function. So basically I've just shown That's what I'm asked to do, that there are at least two computers that are directly connected to the same number of other computers. Question 2, and yes, these get harder as we go. Question 2, we have a set of 9 distinct points with integer coordinates in XYZ space, so three-dimensional. Show that the midpoint of at least one pair of these points has integer coordinates. Now, of course, I could go through and find the midpoints of all of these points, but let's go about this in a mathematical way instead of a plug and chug kind of way. What do we know about integer coordinates? Actually, let's start with what do we know about the midpoint? Well, the midpoint says in order to find the midpoint, we need to take the x value of the first one plus the x value of the second one and divide it by 2. That's what the midpoint formula says. So if I'm doing this for x's and y's and z's, oops, z1 plus z2 divided by 2, that's my midpoint. Notice all of these are divided by 2. So essentially what I'm saying is the sum has to be even. Well, why does that matter? Well, it matters because if I take an odd number plus an odd number, what do I get? I get an even number. If I take an even number plus an even number, what do I get? I get an even number. So that's how I'm going to go about this question. What I want to do is I want to look at the possible parity. So parity just means if it's even or if it's odd. So from the product rule, we've got an even or an odd here, an even or an odd here, an even or an odd here. 2 times 2 times 2 is 8. So there's 8 different possibilities. And now I've listed them here for you, but that's not necessary. So essentially I'm saying it could be an even number, comma, an even number, comma, an even number, or an even, odd, etc., 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 because these are ordered triples. So 8 is essentially the number of boxes. Well, how many points do I have? They gave me 9. So essentially I'm saying 9 divided by 8, which of course means 2 of them must be the same. All right, let's take a look at this last question. During a month with 30 days, a baseball team plays at least one game a day, but no more than 45 games. Show there must be a period of some number of consecutive days during which the team must play exactly 14 games. So again, I encourage you to press pause to try this question all by yourself or with your classmates before you just press play to see the answer. But this one will stretch your brain a little bit. Let's start by saying we know that because they play at least one game per day, but no more than 45 games, that our number of games that they play each day is going to increase. So I'm never going to have 2 days in a row where I've played the same number of games because they're playing at least one game a day. Which means if the first day I play 1 and the second day I play 1, then the second day I've actually played 2, 1 but the day before and 1 that day. So you get the idea. So what I'm going to do is I'm going to let A sub j equal the number of games they've played up to that point, up to the jth day of the month. So A sub j is going to be the number of games played on or before the jth day. Then my series of numbers must be increasing, which we know because it's increasing by at least 1 every day. And they're going to be distinct, which means I'm never going to have the same number twice, because even if I just play 1 a day, that number is different each time that I do it. So essentially what I'm saying is that A sub j must fall between 1 and 45. 1 is the minimum because I'm going to play at least one game on the first day, but I can't do more than 45, so 45 is my max. Now, hopefully that has made sense so far. Now, let's take this guy and just for fun, because we're dealing with 14 games, let's take 1 plus 14, a sub j plus 14, and 45 plus 14. What does that give me? That gives me 15 is less than or equal to a sub j plus 14 is less than or equal to 59. Do you agree that that is still true? Sure, because I just did a simple mathematical task. So if that's also increasing, and those are also distinct positive integers, where this is true, together I've got 60 integers. I've got these, and I've got these, 60 total. But all of them are less than or equal to 59. So the pigeonhole principle says at least 2 of these integers are equal to one another. Well, I know that these guys, none of these are equal to one another, and I know none of these are equal to one another, so essentially I'm saying something from here, which we're calling a sub j, must be equal to something from here, which we're calling a sub, well, let's change the indice because it can't be j again, plus 14. Which I have it written backwards here, but it's the same thing. So essentially I'm saying it's going to go that this is going to be true. A sub j, or let's go ahead and keep it the way I have it in the written out solution here. A sub I is equal to a sub j plus 14, which means exactly 14 games were played from day j plus 1 until day I being some number greater than j.